Hi, everybody. Welcome. It is Tuesday, September 26, 2017, fall semester. We have a crowd full here tonight in Kitty 228. We're here for the circuits exam. Welcome to the home audience. And a big thank you to Sean, the man behind the camera who makes this happen. All right. All of these exams are posted on the course website. What's my goal for tonight? Go through 4 questions that will cover, I think, the key topics we have covered in chapters 1 and 2. So let's get started. So the first file is, it should be posted on the course website, E245 Quiz 1, Version 1, Spring 2017. Okay, so this is posted on the course website. For those of you at home, I can hear you downloading it now. Quiz 1, Version 1, Spring 2017. So let's begin. Let's get it started in here. Okay. Who said super mesh? That was great. Who said it? Way to go. All right. Excellent. How did you know this was a super mesh so quick? Right. You got the current source in the middle between 2 meshes. And it's a super mesh. Perfect. I'll give you a moment to write this down, copy it. All right, now, it says, using mesh analysis. So in this problem, you don't have to worry which technique to use. I tell you. All right, so it says, using mesh analysis, determine the values of I1 and I2. Now, to help us get started, I'd like to, first of all, just quickly think about the problem. Our colleague here nailed it. This is a super mesh. How do I know a super mesh? A current source shared between 2 meshes. Got it. Now, I remember, how do I handle a super mesh? I walk around it. And then I come back and I write the equation for inside the super mesh. So that's good. So that's going to give me 2 equations. However, I have a diamond. And when I have a diamond, I need another equation. So I say, okay, the diamond is being controlled by Vx. So I need to go where Vx is and write another equation. So I'm looking at this saying, great, I'm going to write 3 equations, and then I'm going to have to solve them. So right away, I know my game plan. I sense a question from my colleague here. I sense it. I don't have it, but I know you have a question. Can you help me out?
Okay, I do have a question. Since there's 2 diamonds, that should be 38.
Oh, there's 2 diamonds. I only saw 1. Boy, that's a rookie mistake. I'm glad you're taking this test and not me. You're absolutely right. There's 2 diamonds. So now we need an equation for each diamond. So you are great. I'm glad I sensed, because you were right and I was wrong. All right? So we have 2 diamonds. So I'm going to have to get an equation for Vx and Vy. Perfect. Excellent job. So now I need 4 equations. So let's look at the solutions. Okay, the solutions are posted. Okay. Quiz 1, Spring 2017, solutions. And the first thing I do is we use a super mesh. Now, I won't be giving you this little X on the exam. So you can start anywhere you want. But that's my marker. That's where I start. So, my colleagues, let's write the equation. Now, I'm going to need your help to make sure I don't make a mistake. I start at the X and I walk around. I get minus 25. Then I get plus 20 times I1. Now, I don't come down because that's a super mesh. I keep going around. I get plus 20 times I2 minus BVY. This is a good question. The question from our colleagues in front is, isn't it minus? Okay? And was that your question, sir? Or? Yeah, help me out. What would you know the answer to the question? Should that be a minus 20 times I2?
It's kind of indicating the way that the current's most likely going, although it's not definite. But the current's probably going the opposite way of what it's described, because that's what was in the homework also. But that's giving where the positive and negative of the voltage is.
Right. So, okay, so I like your contribution very much. You're bringing up 2 points. There is I2 entering the resistor on the left. My colleagues, for a moment, forget the minus Vx. If that minus Vx wasn't there, I'm hoping we would all agree that would be 20 times I2 and that would be positive. Do we agree? All right. Bree, are you good? Okay. So it should be 20 I2. Now, I'm going to pause. There's a second thing I could write here. Instead of plus 20 I2, what could I have written? Minus Vx. But it is not minus 20 I2. The current always enters the positive end of the resistor. So if I'm looking at the current is going in on the left as I'm looking at it. So it becomes I2 times 20. That's the direction I'm going in. Now, if you didn't want to do that, you could replace that by saying minus Vx. Am I okay? Okay. So I get minus B. Did I do okay, sir? We're good? Okay, minus BVY. And now I come down on the bottom. Something similar again. I think there's 2 possible ways of writing this. Someone give me one. Plus 20 times I1. Excellent. Plus 20 times I1. Fantastic. How else could I have written it? Minus Vy. X. Doesn't matter which way. It's all going to turn out in the end. And then all of this equals 0. That's one equation. So let me just slide down. Okay. So we get minus 25 plus 20 I1 plus 20 I2 minus B must be 4. B is 4. Minus 4 Vy plus 20 I1 equals 0. Are we good? Now, my colleagues, what can I write? How can I relate Vx to either I1 or I2? Because I want to solve for I1 and I2. Vx is in the way of that. So how can I write Vx in terms of I1 and I2? Or just in terms of I2. Good man, yes, sir. Very close. Very, very close. My colleague, I'm glad you said that. This is excellent. So what we have, since I can't reach up there, let me draw it. We have this resistor. This is minus plus Vx. Now, help me out. I2 is going in this direction, and this is 20 ohms. Now, if I were to, for the moment, hide Vx and say, what is the voltage across this resistor? The current enters the positive end. So it's positive, negative. So this voltage is I times R. So 20 times I2 is the voltage positive to negative over this resistor. Vx is minus the positive, so Vx is minus 20I2. Sir, did I get it? Are we all good on this, my colleagues? Any doubts? Now's the time. Right, you can say it one of two ways. You can say Vx equals negative 20 times I2, or equivalently, as you just said it, minus Vx equals 20 I2. Are we good, sir? We're good? All right. Now, that's the second equation. Who can help me out? I need a volunteer. What is Vy? Sir, help me out. What would we write down for Vy? Right. Vy is negative 20 times I1. Perfect. The current I1 is entering this side of the resistor. From the current's point of view, that's the positive side. Positive, negative. Ohm's law. I1 times 20. Positive. Vy is flipped. So therefore, Vy is minus 20 times I1. Did we get it? That's three equations we have. This one up here, and the equations for Vx and Vy. I have only one more equation to go, and that's the equation in the super mesh, the actual branch itself. Who wants to help me out? Mr. Milan. Mr. Milan, take your time. This is a little tricky here. You're going to do it. Tell me, how can I relate I1, I2, and AVX? I think that's right. Here's how I see it. Hold on to that. I would say, since AVX, that's AVX, since AVX points up, that's I2 minus I1. And I think that's what you said, wasn't it? All right? If I1 was 0, AVX would be I2. But I1 is not 0. So AVX is I2 minus I1, going in the opposite direction. Mr. Milan, did I get it? All right, good. Sir? See, I don't know if that always works. The question is, could you put yourself in the node at the top? Really, we're saying the current in this branch has to be AVX.
Well, it would be like I1 plus AVX equals I2, because I1 is flowing like along the top of it, and AVX is added to it.
Yeah, I see what you're saying. You're saying if you go in the node, I1 goes in, AVX goes in. The problem is the way I1 is defined is a mesh current. It's also coming out of the node. Some people might find that confusing. If I look at it this way, this current has to be AVX. That's I2 minus I1. Did I do okay? My colleagues, there you have it. Those are the four equations. Now, the rest is algebra. I go through this step by step. Vx is minus 20I2. I substitute all this in. This was not hard. I2 minus I1 is AVX. A is 2. My colleagues, I'll leave the rest to you. But now you solve all the equations and you get the two values of the current. So the challenging part was to know to write 4 equations and to recognize it was a super mesh, and then to get the equations for Vx and Vy. How did we do? You got mesh? All right. Question 2. Nodal. You can do it. No. There is. But I didn't make this a Thevenin problem. This is a nodal problem. Because I'm not asking for the resistor for maximum power transfer. I'm just asking for voltages. We could turn it into a Thevenin. Well, or an equivalent circuit. Does Thevenin always apply to max power? Yes. Does it also apply to a simple equivalent circuit? Yes. All right. My colleagues, we look at this and let's have our battle plan before we rush off to solve it. Does anything strike you about this circuit? I think I see a supernode because there's a voltage source between 2 nodes and neither node is ground. Sorry?
No, there's only one.
There's just one supernode. And it's a voltage source between 2 nodes with neither node equal to ground. So that becomes our definition of a supernode. So I got a supernode, and I got a node on the left and a node on the right. And I got to do something down here that looks a little messy. So I see at least 3 nodes. 1, 2, 3. And do I have any diamonds? Thankfully, only 1. So there's another equation up there. So I'm thinking, okay, you got this. Now let's look at the solution. All right. Notice what I did here. All the dotted lines are added. All right, you got to add them if you want to solve it this way. So I called the node on the left V1. I clearly identify the supernode. And on the other side is V2. And I think later on, I'm going to go for a walk through the supernode. So I go plus and minus V1. And over here, plus and minus V2. So I say, all right, I'll worry about this a little later. So I'm thinking 1, 2, 3 nodes, 2 nodal equations. And then I need an equation for the diamond. Are we good? Good. All right. So let's begin. I put myself on the left side of the supernode. My colleagues, if I do something that doesn't make sense, please stop me. That's minus 5 plus V1 over 10. That's V1 minus 0 over 10. Plus another V1 minus 0 over 10. plus V1 minus 0 over 10. 1, 2, 3. Now, I'll get back to the supernode, but I'm not done yet. So I'm going to jump over here to the other side. Now this becomes V2. I get V2 over 10. V2 over 10. This current is flowing out, so it's plus 2. Let me pause. I'm not done yet, but I'm sensing there's questions in the air. Can I be of any... How can I help? Great. Why didn't I use Vx? I could. I could have. I personally would have found it a little confusing. Vx is minus positive. I'm used to thinking of the current going from positive to negative. And that's consistent with the definition of V2. So you're right. Later on, I'm going to have to come back and find an equation for Vx. But right now, the first pass, I find it easier to ignore it and go with either V1 or V2. In this case, V2. Did I do okay? Great. Thank you. My colleagues, anything else? So I'm up to plus 2. Now, the last term is V2 over. Now, I know I got this V out that I got to get back to, but I see 20 and 5 in series. So I say this is V2 over 25. So I get V2 over 25, and all of this equals 0. This is the first nodal equation. Devin, how can I help?
Why is it not V2 minus V out over 20 instead of V2 over 25?
Devin, what you said is absolutely correct. Devin, another way of writing this problem is the current through this last branch is V2 minus V out over 20. You're absolutely right. Now, that introduces yet another unknown. So here's how I approach this problem. If I know the value of V2, I can use voltage division like that to get V out. So for the time being, I'm ignoring V out. Confident, Devin, that if I can solve for V2, it's a one-liner to get V out. All right. So, my colleagues, are we all good? All right. Now, with the supernode, you might remember, okay, voltage source between two nodes, neither node is ground. Boom, we have to do this. Now, the next thing is I have to walk through the supernode. I cannot solve this problem without including AVX. So I have to walk through it. Now, before we walk, we prepare for the walk. And what I do is I say, this is V1. Positive, negative. How do I know it's negative? It's ground. And I got two groundskeepers, one in each section. That's going to give me a hard time if I don't put ground. All right. So, plus minus V1. Likewise, plus minus V2. So now, I put an X here. I start here, and my goal is to walk through that node, that dependent source, so I can get an equation for it. So I start here, I get minus V1. Minus AVX. Then I come down. Now, my colleagues, to my colleague who asked this question before, I could now say minus Vx. Absolutely. But I'm going to write it as plus V2. But either way will get you the right answer. So I write this now as plus V2. And all of this equals 0. It's starting here, going around and coming back through the supernode. I know what you're saying. V1's on the left, V2's on the right. If you can see it right away, that's great. But if you can't, take a walk. This whole thing is V1 from top to bottom. The whole thing from top to bottom on this side is V2, plus, minus. So just take a walk. Make sure you don't make a minor mistake. We're good? Now, my colleague who asked this earlier, I think you already know this, so I'm not going to ask you, but this goes to your point. I now have to get an equation for Vx. So what I have to do is look, where is Vx in the circuit? Here. Now, what am I solving for? V1, V2. So I want to get Vx in terms of V1 or V2. So I look at this and say, wait a minute, Vx is from here to here, so is V2. The only difference is Vx is minus positive, and V2 is plus negative. Vincent, you're nodding your head. Can I put you on the spot? V2 is minus Vx, or Vx is minus V2. Bravo. Do we now have all the equations? Devin, I'm thinking of you. The game plan here is solve for V2. Then I'll get V out. My colleagues, can you write these equations? Now, the next thing how can I be of assistance?
Okay, in the first equation, why are you using current, and in the second equation, you're using voltage?
Excellent. That's an excellent question. The question is, why am I using all current here and voltage here? That's because I started out doing nodal analysis, which is current. So this whole equation is the left side and the right side. Now, why do I have to use voltage? Because I got a voltage source between two nodes, and I got to go through it with neither node ground. I got to go through that somehow to pull it into the equation. So you're very good to notice this is KCL. And well, this is nodal, this is mesh. That's the best way to say it. Well, if that voltage source was a current source, that would change the problem completely. We wouldn't have a supernode. So the point I'd like you to take away from your question, because it's great, when you have a supernode, you got to take a walk through the supernode, and that's voltages. Did I get it? All right. Yes, how can I help? I don't. The question is, when I'm solving for the supernode, how do I know to start at the x? I don't. What I know is I have to walk through the supernode. So my colleagues, start anywhere you want. Start anywhere you want, you'll get the same answer. How about you start up here? You get minus AVX plus V2 minus V1 equals 0. Same equation. So don't worry where you start. Make sure you go on the right path, which is through the voltage source. Did I do okay? I still see some questions. Can I be of any help? You sure? Are we good? Yes. Good. First of all, go to where Vx is in the circuit. My goal is to solve for V1 and V2. So I'm looking for something to relate Vx to V1 or V2. I look at this and I say, wait a minute, this is V2 right here across this resistor. And V2 is positive, negative because of ground. Look how Vx is, minus, positive. They're both across the same resistor. They're just defined differently. Minus plus or plus minus. So they're the negative of each other. Did I do okay? 2 thumbs up. Beautiful. Thanks. All right, my colleagues. I go through this step by step. I don't miss a step. Take these 3 equations. Now, save, Devin, I'm thinking of you. Save some time on the exam. My colleagues, I don't care what V1 is. I want V2 because I'm looking for V out. So get rid of V1. Right, when you solve these equations, you're going to have to substitute, right? Get V1 out of there. So you get everything in terms of V2 and solve for V2. I'm not asking you what V1 is. V out. He's asking for V out. So whatever V1 is, I don't care. Get me V2, then I'll get V out. My colleagues, please don't neglect the minor stuff like solving algebra. Make sure you go through these problems and make sure you can get a solution. I get V2 is just around 4.054 volts. Okay? Now that took a little bit of time. That took a page, but you can do it. I tried, if you can set up these equations, I know you can do it, just practice. Now, Devin, I want V out. So I say, wait a minute, I know V2. Last part of the problem. Now, my colleagues, the people before you, this is where they stumbled. They got V2, and they didn't know how to get V out. Or they somehow threw V out in here and got all mixed up. If I know V2, what I have, and let me draw it over here so you'll see it. From here to here is V2. V2 is across both of those resistors, the 20 and the 5. Now, I'm taking V out here. V out's an open circuit. There's no current here, open. So that means all the electrons that go through the 20 ohm go through the 5 ohm. They're in series. Voltage division. All right, so what's V out? V out is what, 5? It's 5 over 20 plus 5 times the value of V2. That's it. You're done. Sir? Good. This A was given. No need to calculate it. This was given. My colleagues, that's it. Are we good? We have a part B coming up. Yes, sir.
Can you also have done like V2 over 25 is equal to V2 minus V out over 20? Solve that.
Say that again.
Could you have done V2 over 25 is equal to V2 minus V out over 20?
V2 over 25. That's the current.
V2 minus V out all over 20.
Yes. You could also do this. Okay, because what you're saying, V2 over 25 is the current through these two resistors. The current through these two resistors are the same. So how else could I calculate the current? The current through the 20 ohm resistor is V2 minus V out over 20. That should give you the exact same answer. All right, next part of the problem, part B. Okay, let me not look at the solution yet. Determine the power supplied by the 5 amp current source. Determine the power supplied by the 5 amp current source. Oh, there's the 5 amp current source. How do I figure out the power? Now I got to find V1. Huh? Excellent. So you're telling PIV, power equals current times voltage. Is that what you're saying? I love it. All right. So I have the current. I now got to get V1. And I love this. How do I get V1? I know V2. So somewhere here, 3V2 equals V1. I got it. So now I know V1 is a third, V1 is 3 times V2. I know V2. I should have just quit at the yep. So here, V1 is now 12.162 volts. Now let me draw this to make sure we're okay. 5 amps. The voltage is plus and minus 12.162 volts. So how much is the power supplied by the current source? I times V. That's it. I sense I'm losing some people, my colleagues. Now, technically, we should have a negative sign because it's giving it away. But I said I'm putting our colleagues through so much. Give them full credit even if they don't have the negative sign. So as long as you did I times V and got 60.81 watts, you're in. All right. That's problem 2. How's he doing? Okay. All right. Good. Anything else, my colleagues? All right. Yes, sir, in the back, my right fielder. No, only abacuses. Calculators are more than welcome. Good man, so bring your calculator. Problem 3. Now, before we even look at problem 3, I've given you mesh, outside fastball. I've given you nodal, up high. What's coming next? Thevenin or amplifier. Those are the 4 topics. Mesh. I mean, look, I can ask you anything. I don't want to limit myself to these 4. But these 4 are like, they're pretty important, okay? So mesh and nodal we've done. Let's bring in the amplifier. Da, da, da. Tell you what, let me show you the... There. That's what you'll get. How we doing so far? How's he doing? Is he doing okay? Okay, good. Sean, how's it going back there? I'm walking into the audience to see how everyone is doing. We have a Manchester United fan here. All right. Well, what's one of the songs? Glory. No, it's when the Reds go marching in, right? Yeah. Right. Glory, glory. Yeah, there you. Glory, glory, Man United. There you go. There you go. We have the Stevens Athletic Department back here. All right. This is very good, and we have Flash with us tonight. And my front row colleagues who got bumped to the back. Next time, review 2. I'll reserve the whole. We'll put a rope. We'll put the red rope. All right. We'll have the guy in the tux. You know, only you. All right. Now, do you know what that shirt says? Because I don't.
I have no idea.
But it's Japanese.
Yes.
Good man. All right. Now, for those of you who have suffered through the problem of the week number 1, you should look at this and say, bring it on. I'm ready. All right? So, I looked at this and I said, Kevin, there's an REQ left and there's an REQ right. So let's start on the right side. Now, by the way, I'm looking for V out over VS. So just like in the problem of the week number 1, I'm tempted to start over here. I'll get V out in terms of I in. And then I jump over here and I'll get I in terms of VS, and I think it should work out. Now, for all of you who saw me during office hours or came to class that one day, here's the key thing. All of this current stays here. And all of this current stays here. All right? So in that sense, they're separate. However, this is a dependent source. So whatever the value of I in is, it multiplies it by A, which is 15. And to my colleague in the back, A is given at 15. So the first thing I do is I say, let me get an REQ right. Now, there's more than one way of solving it. You could use current division here. But let me do the REQ right. REQ for 2 resistors in parallel. Please, no one get this wrong. Product over sum. So I get 9.375 ohms. Now, if that's the case, I no longer see 2 resistors. I see 1. And that 1 resistor is 9.375. Now, I tried to trick you here. So beware. Right? That current is flowing down. So when it comes over here, which way does it go? Up. The opposite of what we would expect. Positive, negative is supposed to come down. So what is the value of this voltage? Ohm's law. AI in times REQ. However, there's a minus sign. Yep. So we got AI in times 9.375 equals V out and I get V out is minus 140.625 times I in. We're about halfway through. How are we doing? Now, I'm supposed to get V out in terms of VS. I got V out in terms of I in. What do I need? I in and VS in an equation. So I desperately search and say, where is I in? Left side. Where's VS? Left side. We can do this. I see another 2 resistors in parallel. I call it REQ left. 25 times 10 over 25 plus 10. Product over the sum. And I scroll down. I now get an REQ left of 7.143 ohms. Now stop me if I don't make sense. 7.143 ohms. I then say, great. I now use voltage division. Devin, for the second time tonight, we're using voltage division. So I say, wait a minute. How can you use voltage division? Not all the resistors on the left are in series. So what do I say? Exactly. The REQ has combined these 2 resistors. So, my good man, I no longer see these 2, I see 1. And that REQ is in series with the 10. So I say, great, how do I get, let me just erase this. How do I now get V1? V1, which I define to be across the REQ, is gotten as REQ over REQ plus 10 times VS. How am I doing, sir? So I say, good. That's REQ left. Good, I heard that question. That was very good. This is REQ left. REQ left. Am I doing okay? All right, so my colleagues, I now get Shannon, I'm thinking of you. How are we doing back there? All right. So Shannon, I now get V1 in terms of VS. Great. But that's not what I want. I want I1 in there somehow. But I say, wait a minute. Wait a minute. Hold it. Hold it. I in. Oh, wait. I go back. Oh, I in is through the 10 ohm resistor. So V1 also equals 10 times I in. V1 is 10 times I in. And I say, I think I got it now. I slide down here and say, I in is V1 over 10. What's V1? I already got that. So I now have I in terms of VS. We're just about there. What I'm now going to do is take this equation and plug it in for I in at the very top. You see that? V out equals minus 140 times I in, but I in is 0.0417 times VS. Take this, put it up there, problem done. I'll show you on the next page. How are we doing? All right. So I look at all of this and say, okay. I then get that V out is now in terms of VS. And there it is. How are we doing? How can I help? V out over VS. But you know what? That was only part A. Let's see what part B is. Oh. No, no, no. This has to be illegal in New Jersey. No, no. This is not allowed. Wait a minute. You get a value of Vs is 5 volts, okay. A load resistance, no, no. Is placed between terminals A and B, no. You can't combine an amplifier problem and a Thevenin problem. Yes, you can. We want to select the value of the load resistance which result in maximum power with limit load resistance. Determine the value of the load resistance for maximum power transfer. What type of problem has now this suddenly become? Dun, dun, dun. It's now a Thevenin problem. All right. So you got like 12 minutes left in the exam. You're on the last problem. And I throw you a hardball outside the plug. Maybe you jump, and you say, Thevenin. Okay. So what do you write? You just start writing down stuff. You go, R Thevenin is V open circuit divided by I short circuit. And what do I know? For max power, R load equals R Thevenin. Okay, okay, so far so good. Take deep breaths. Now, V out in this circuit is V open circuit. Wait a minute, to my colleague in the back, you know, like, what's the question? I love that question. So, we're placing something between terminals A and B. So where's V open circuit? Between A and B. That's V out. We already got that. Done and dusted, as they say in England. All right? That's it. V out is V open circuit. Good. So what do I know? V out over V source is this. I now tell you. I tell you in this problem. V source is 5 volts. I now know that V out, which is V open circuit, is minus 29 volts. We're good? The only thing left to do is I short circuit. Now, I got to go back. I got to go back to the circuit. Ah. Aha. Ah. All right. Where do I put the short circuit? Right here. What is the value of the short circuit current and why? By inspection. Minus A times IN. Now, let me say that again. If I put a short circuit, a wire with 0 resistance between A and B, how much current is going through the 15 ohm resistor? 0. I love that. That's good. I like that. 25? 0. So that means all this current, Christina, all this current is going through the I short circuit, which is minus AI in. So I short circuit is minus AI in. Now, I know what A is. That was given. I in. So I say, wait a minute. From the first part of the analysis, I know that I in was this, and Vs is 5 volts. So I now know what I in is. I get I short circuit. R Thevenin is V open circuit divided by I short circuit. And that's it. How do we do? Note to TAs, the result may differ slightly to rounding. Can you believe it? There's a part C. What? Before we get to part C, exactly. Yes, it is. Excellent. You can make up the exam for me. All right. So, my colleagues, now, here, before I show you that, are we okay on A and B? All right. Now, what part B of the problem did, and this is so beautiful. I know when you have the stress of the exam, it's hard to see this. We have taken a complicated amplifier circuit, and from the outside looking in, it's V Thevenin, R Thevenin. That's it. Now, I ask you to put a load resistor here. There's only one value of load resistor in the entire world that will give me maximum power. Our load is R Thevenin. Now, how can I get the power? One line. Don't forget this is one line. Don't memorize it. Understand it. Power is V squared over R. What's V? Half V Thevenin. Why? There's two resistors of equal value. V Thevenin over 2 squared divided by R. You can write it as R Thevenin or R load. They're equal. My colleagues, that's it. I was feeling very generous. I said, even if they got the wrong value for R Thevenin, if they showed they know this, give them full credit. I was too soft. I know. I know. Never again. One more time? All right. All right. My colleagues, I was going to go over a fourth problem. I didn't realize this was also Thevenin. So we've done it. So look, there's 4 major areas. Before I summarize, my right fielder in the back, help me out. Yeah. Your questions help me. The question is, could I use I times V here? Absolutely, you can. However, you now have to solve for I. Now, you could also use I squared R. But again, you got to solve for I. This is the easiest because V is always, for power, maximum power transfer, V is always V Thevenin over 2. Done. You'll get the same answer, but it's an extra step. Now, another question from my colleague here. Did I get your question? We're good? Right. How did I get V open circuit? 2-part answer to your question. V open circuit is V out. We solve for V out in terms of Vs. Here. V out over Vs is minus, let's say minus 6. Then I told you in part B, Vs was 5. Did I get it? All right. Part C. Oh, we did it. The end. My colleagues, anything else? Was this helpful? All right, listen, I'll be thinking of you over the weekend because I'll be making up the exam. Thank you, Sean. Thanks, everybody.